Okay, I'll get started. I wanted to start with a couple of reminders for you, um, or announcements for you. One is just a reminder about my email here, gorange@pa.uky.edu. That's the best email to get hold of me. It's the one I mostly look at. And I wanted to remind you that I had my first office hours yesterday, but this will be my schedule for office hours on Tuesdays and Wednesdays at 2:30 and 3:30 respectively. So last class, I thought the chat worked quite well. You can ask questions there. So I'll try and continue this class to monitor the chat. And certainly you should feel completely free to put all your questions there. You could also raise your hand if you wanted to raise your hand, but last class it all seemed to be through the chat box. I wanted to just remind you about the homework cycle and the way the homework cycle works, because I got some questions after I described it on Tuesday, and probably I didn't describe it that clearly on Tuesday. So on Wednesdays, the homework is collected at midnight in two different forms. So you have to have submitted your numerical solutions to all of the problems on WebAssign by midnight on Wednesdays. And you also submit a fully worked out problem, with equations, with diagrams, with calculations onto Canvas by midnight on Wednesday. And your recitation instructor will tell you each week what particular worked out problem they are collecting. So the WebAssign collection and the Canvas collection are from the same homework set. They're published both on Canvas and they're published on WebAssign, but they're two different forms. One where you just answer the give the numerical answers on WebAssign, and where you do the full working out for the Canvas submission. So I hope that's a little clearer now. As I mentioned, this week's quiz homework assignments are all practice quiz homework assignments. They won't count towards your grade. They're not going to be part of your final grade, but they're preparing you for the quizzes and homework starting next week that will count towards your final grade. So I hope that's a little clearer. Let me just look in the chat here. Isabel, when will the grade on WebAssign be uploaded onto Canvas? Or how do we know you can see our WebAssign grades? That's actually an interesting question. So the WebAssign grades, as I've got it set up now, are not automatically transferred to Canvas. But I'm going to talk to our Canvas Cengage rep about whether I can change that so that they're automatically transferred to Canvas. So that way you would then be able to see, check that we've got your solutions. Let me. Questions are running away from me. So in WebAssign, the questions are probably labeled just 1 through 10 or whatever, or 1 through 6 or whatever, rather than the question numbers corresponding to question numbers in the book. In Canvas, what I posted is the question numbers according to the book. So all these questions that are in WebAssign and posted on Canvas, they're the same questions, but WebAssign may be labeling them 1 through 6, whereas the book they're not 1 through 6. There's some collection of numbers. And so I'm trying to give you both ways to locate them, find them. If you have any problems with that, let me know. So there's another question, Isabel. Does the homework submitted yesterday or each week to Canvas have to be a PDF, or could it be a picture? So PDF is best for the graders. It's easier than pictures for the graders. But if you've got a JPEG, for example, from a picture, there's lots of free apps for phones or computers that you can convert it into a PDF. So it would help us a lot if you at least convert it into a PDF. Okay. So let me move on here. Today's class, I want to talk about the mathematical description and the graphical description of motion. So the whole class is going to be about how we describe motion, the physics language for describing motion. The first few slides I got here, I think it's 3 slides, just walk us from a kind of big picture of motion in physics to the specific questions that we want to answer today about describing one-dimensional motion. And then the remaining slides, we're really going to look at the elements, the components of our language for describing one-dimensional motion, bit by bit, part by part. Okay, so the first thing I want to introduce was 2 terms, kinematics, dynamics. Those are terms, physicists always use kinematics, dynamics terms. So I just want to let you know what those terms mean. So kinematics is the sort of science of describing how things move. You know, whether something's going fast or slow, or speeding up or slowing down, is described with kinematics. Kinematics is a language, and the components of the language we're going to meet today is things like displacement and velocity and acceleration. So that's kinematics, describing motion, and that's what we're going to begin now. And then dynamics, that's describing why things move. It's explaining why things move. It's understanding why things move. So we understand the way things move the way they do in terms of concepts like force, in terms of concepts like energy, in terms of other concepts. And that's dynamics. So the way I think of it is that sort of kinematics is this sort of foundation for describing motion. And then on top of that is dynamics for explaining motion. And it's kinematics we're starting now today, and it's dynamics what we're going to move on over the next couple of weeks. Then finally, in introducing today's material, I want to say a few words about one-dimensional, two-dimensional, three-dimensional motion. So space is three-dimensional. But in physics, we typically abstract problems to either one-dimensional motion or two-dimensional motion. So for example, motion along a straight line is one-dimensional motion. Motion around a circle is two-dimensional motion. Now, space is three-dimensional, but we can sort of pull apart the interesting motion from the background by thinking of just the motion in one dimension when it's straight line motion, and the motion in 2 dimensions, for example, when it's circular motion. So we're going to begin our work today really with one-dimensional motion. So that's this topic on the left here. I'm trying to use this drawing pad. I as soon as I pick up the pen for it, I feel like I've become a 2-year-old and I'm completely out of control with it. But I'm going to work on this for a bit. So we're going to start over here on the left. We're going to be talking about today in the next class, one-dimensional motion. And, you know, an example of it would be, for example, these sprinters. I'm in here somewhere. We're going to run in a straight line. That's one-dimensional motion. We only need one dimension of space to describe that one-dimensional motion. And specifically, we can describe whether we're going left or right or up or down with plus and minus signs. Now, another type of motion that we'll talk about is over here. Here comes the 2-year-old again, is two-dimensional motion. Now, if I were to punt a football, God forbid, you know, but if I did, that would be, it would go in a curve that we call a parabola, and that would be an example of two-dimensional motion. The motion is occurring in 2 of the 3 space dimensions. If I was to make a basketball shot, again, God forbid, that would also be an example of two-dimensional motion. The basketball, although space is 3 dimensions, the basketball itself is moving in 2 dimensions. So we're going to be doing one-dimensional motion today and next class, and we're going to be doing two-dimensional motion later. Okay, this needs to be cleared. So today's class, I really want to get through this language of motion, this description of motion. We're going to talk about position, displacement, distance. That's sort of how we describe how close or far something is. We're going to talk about speed and velocity here. That's how we talk about how slow or fast something is. And then we're going to talk about finally acceleration. That's describes whether something's speeding up or slowing down. Look, you have already an everyday notion of these quantities that describe motion. All I'm doing, the only reason I'm here is to put some sort of rigor, make more quantitative description of, you know, whether something is close by or far away, whether something is fast or slow, whether something is speeding up or slowing down. And we're going to do that. We're going to do that by writing down equations to describe these quantities. We're going to look at examples of these quantities, and we're going to draw some graphs of these quantities. Okay, so I want to start with a little demo because I'm going to show you some motion, and we're going to look at displacement, velocity, acceleration, bit by bit in the context of this demo. So let me see if I'm capable of doing that. I think I've got to firstly change the window I'm sharing. So I'm hoping you see a different window now. And now this window shows you the chemistry physics lecture room that we would have been in. And that makes me kind of sad. But we're not in there, but I'm going to show you this demonstration anyway. In the center of the screen is a device called an air track. And on that device is a cart. And the cart can float frictionless on the air track. And it can move frictionless on the air track. And we're going to look at an example of motion. Now, I've added to the video, again, I did this with my drawing pad, and it turns me into a 2-year-old, some locations. So in the center here, I'm going to call this the origin. And so I labeled it with O for origin. And then you see on the left and right, plus or minus 1 meter. So that's 1 meter to the left and right of the origin. And then you also see I've marked out plus or minus 2 meters. And so let's watch the motion that we're going to explore today. It's all about this one little example. And here we go. So that's a motion that lasted about, I don't know, a little under 20 seconds. And I'll play it again here. I started out over on the far left at -2 meters from the origin, and the car eventually got to +1 meters from the origin and then rolled backwards. And then I finally stopped it at -1 meters from the origin. And what we were watching was, the position of the car. We were watching the velocity of the car. And we're also able to see the acceleration of the car, whether it was speeding up or slowing down. And we're going to work on describing all of that quantitatively. So now I need to go back to the other screen. Which I hope you can see. Tessie, my dog here, will come to a number of lectures when we have demonstrations, and also sometimes the handouts. So you'll see her a bit. First thing I want to talk about before we actually get into the guts of displacement, velocity, acceleration is just to introduce the concept of the reference frame or the coordinate system. Reference frame or coordinate system, I mean the same thing. They're just different phrases, different ways of expressing the same thing. And what they mean is, really, we imagine them as kind of arrays of meter sticks and arrays of clocks that help us measure the motion of things, the motion of objects, the motions of bodies through space and time. And so that's what a reference frame is. That's what a coordinate system is. And what we're going to be talking about here is one-dimensional reference frames. And so I've sketched on this slide here a one-dimensional reference frame for us to look at, and we're going to get used to these sort of sketches. So over in the center here, this little guy, that's the origin. I'm going to call the position of, in the reference frame, I'm going to call it X, and that's where X is 0. That's where we're at the origin. And then if we go over towards the right, here I'm walking towards the right, that's towards increasing X, more and more positive X. And then if we're over here on the left, as you walk towards the left, you're going to more and more negative X. And so the reference frame allows us to say where we are, whether we're close by the origin or far from the origin, that sort of thing. I've added, sorry. I've added a point on this sketch of the reference frame. Here it is. Here it was. And that point is, I just picked a point. It was actually the most rightmost location of that cart as it traveled left to right and then back to the left again. And the cart got to that 1 meter location from the origin after traveling for 11 seconds. And so we'll often do this sort of notation. What I'm saying here is that by X and T, I mean the position and time of the cart. And I'm saying that at the time 11 seconds, the cart was at 1 meter from the origin. And so that's how we can quantify the location of the cart at different times. Okay, so let me go back to the another shot of another demo. So let me just run this for you. this is the same motion, but all I've done is marked in blue, again with my 2-year-old writing, the location of the cart at different moments in time. And specifically, I'll play it again. X1 is the initial location of the cart, and it was at -2 meters. X2 is this kind of intermediate location of the cart when it got to the rightmost point, that was +1 meters. And then X3 is the final location of the cart when I picked it up, and that was -1 meters. So we're going to come back to that. Okay, so let me go back to the presentation. I realize I'm sharing my whole screen, which I mean, that's fine. I didn't want to always, I've shared my emails with people before, so I'm going to go and just share the PowerPoint rather than share my emails. So here I sort of added to the reference frame or the coordinate system, I've added the motion of the cart. I've tried to depict the motion of the cart on this slide. So, you know, here's where the cart started. These are the X and T coordinates initially. I called them X1, T1. Here's the rightmost location of the cart, where it turned around, and I called that X2, T2. And then here's the final location of the cart, called that X3, T3. That's where I picked up the cart. And I'm introducing our language for describing either what we call the distance or the displacement of the cart. So in physics, we'll talk about displacement sometimes up here, and we'll talk about distance sometimes down here. And these are actually different quantities in physics. They may be very similar in everyday language, but they're different quantities in physics language. So the displacement, I've called it delta x. That's commonly what we call it. And it's equal to the final position of the object less the initial position of the object. And its dimensions are length, its units are meters. So that's displacement. Distance, on the other hand. Distance is the length of the path between the initial and the final positions, the total trip taken between the initial and final positions. And that's also got dimensions of length, and it's also measured in meters, but it is distinct. And I'll show you how it's distinct, very distinct in a motion. So for our cart, right, it moved left to right, and then it moved back from right to left. And on the next slide, I'm going to think about distance and displacement for the cart for the entire trip. So let's try and do that. Let me clear this. Let me go to the next slide. Oh, okay. It wasn't the slide I was expecting, but that's fine. It'll be on the next slide that we're actually calculate distance or displacement. This one illuminates, you know, distance and displacement and position a little bit more. It's a graph that we'll often draw when we think about objects moving through space and time. So look at this graph. Let me get the pen working again. So the horizontal axis on this graph is time. The vertical axis on this graph is position. And so this is a time versus position graph of the cart. Now, there's a little red point down here. I called it X1, T1 because that was the initial position at the initial time for the cart. It was at -2 meters, and that's where I started the clock.
Lectures.
And then here's the here's the intermediate position where the cart got to the far right. It got there at 11 seconds, and the far right position was +1 meter. So that was that intermediate position. And then finally, here's the final position. The final position, the cart took 19 seconds for the entire journey, and its final position was -1 meter. So those 3 points that I picked out on the little video, on the little demonstration, are these 3 points here. But this black line, really, this curve really describes the entire motion of the cart through space and time. Any point on this line, any location on this line tells you the position of the cart at that particular time. So for example, it's telling us here that at about 4 seconds, the cart passed through the origin. And also over here, at about 17 seconds, the cart passed through the origin too. There's a lot of information, a lot of interesting information about this, the cart's motion in this graph versus position plot. Okay, I'll clear that and I'll go on to the next slide. And on the next slide, I've just annotated the slide with those 3 sets of coordinates. When the cart started, the intermediate position of the cart, and then the final position of the cart. And the question says, find the displacement and the distance for the entire trip. The entire trip is, according to these red arrows here, cross to the right and then back towards the left. So this is a question really about the distance and the displacement to get from this initial position to this final position here. So let's do those calculations. Displacement. What's the displacement? Well, the displacement, we gave that the symbol, oh, sorry. Let me get my pen. The displacement, delta x here, that's the difference, if you remember from the definition, it's the difference between the final location and the initial location. So final location is x3 for the entire trip. Initial location is x1. And if I fill in the coordinates of x3 and the coordinates of x1, -1 meter, -2 meters, and I'm careful about the signs here, then -1 minus -2 is actually +1 meter. And so the displacement for the entire trip is that the cart moved 1 meter in the positive direction, that's the direction towards the right, for the entire trip. How about the distance? So downstairs here is the distance. And the distance, remember, is the total path that the cart took. So the way I calculated the distance was to think about the first part of the journey, which is to the right, and then the second part of the journey, which is to the left. So the total distance is the distance for the first part of the journey to that intermediate point 2, plus the distance from the intermediate point 2 to the final location. So I'm going to add up those 2 contributions. The first contribution, the distance from the far left to the far right, that's x2, that's the size of x2 minus I1. That's what the vertical lines mean. And then the path length for the second part of the journey from x2 to x3, that's the size, the magnitude of that path length between the rightmost point and the final location. So the path from the left to the right is 3 meters. It's this length of this arrow here, the lower one. The path from the right to the left is 2 meters. It's the length of this arrow here. And so if you add them up, you get a total distance of 5 meters. And so 5 meters is the distance traveled. 1 meter was the displacement. And that illustrates the important difference between those two. Let me go and look at the chat, because I've been ignoring the chat because I'm so stressed about moving from screen to screen, and see if I can answer some questions. So there's, well, I don't want to answer too many turn this into a WebAssign session, but yeah, there are 2 weeks, I think, of free access to WebAssign. Why is the initial location not the origin? Ashton asks that. That's an interesting question. You've got the choice of whether you decide to call the initial location of the origin or not call it. I could have done the problem with the initial location being the origin. I just chose to do it with the initial location not being the origin. And so the choice of the origin is a choice you make, and it's a very good question. Where are the subscripts 1, 2, and 2, 3 coming from? The initial location I labeled as 1. The intermediate location I labeled as 2. The final location I denoted as 3. So those are the 3 distinct locations in my sketch. And when I think about the distance from the initial location to the intermediate, that's between x1 and x2. And so that's why I labeled it D12. And when I thought about that second portion of the journey, from the intermediate location to the final location, that's from location 2 to location 3. That's why I labeled that distance with the subscripts 2, 3. So that was just a notation that I invented. I mean, I think it's a perfectly okay notation, but it's a good question. What do they mean? Tyler, what do the 1, 2, and 2, 3 represent for the Ds? I think I've just explained that. And if I haven't, then we can chat at the end. Okay, let me clear this stuff. And let me move on to the next slide. And the next slide is to remind me to do a little quiz. So I'm going to, give me one moment here, and I'll start the quiz for us. I want you to go, I've got to publish it. I want you to go into Canvas, into the assignments, into the lecture quizzes, and in a moment, a quiz should appear. And I'm going to give you a few minutes to do it. I've got to set a time on it first, so it takes me a moment to do that. And so I believe that I have now published the quiz. And so I'm hoping that you can see the quiz. If you can't see the quiz, stick it in the chat box. And you have to 13:07 to complete the quiz. Okay, so I'm watching the responses, and I got about 130 responses out of about 170 of you right now. And so in a moment, the quiz will be open for another minute, but I'll just move on. Okay, looks like most of you, the vast majority of you really got this. So the correct answer is that the displacement is greater than 0, but the displacement is 0. So if I walk to Starbucks from my house and then I walk back again, the initial and final positions are the same. So that's 0 displacement. However, that's not a 0 distance. The distance is the mile, in my case, that I would have had to walk to Starbucks, so I would have driven, but and then the mile plus the mile that I would have had to walk or driven back. It would have been a 2 mile distance, but a 0 displacement. Okay. So this is what, again, we're lucky to have Lady Gaga in class, and she wants to reiterate this point that distance and displacement are different. In fact, we'll meet this more later on, but displacement is a vector quantity. It has a direction as well as a size or a magnitude, whereas distance is a scalar quantity. It has no direction, it just has a magnitude or a size. And if you, for example, walk around Willie T. Library and return to where you started, that's 0 displacement, but you have walked about 120 meters when I tried it out. Okay, I want to go back to the card demonstration again now, and we're going to talk about speed and velocity. So that means I'm going to share something else. And here we go. So I'm repeating the demonstration. I did this so many times, as you can imagine, to get this right. And it's not easy because I've got to get it to stop at exactly that same place. But I got well practiced at it. But on this particular overhead, or this particular video, I marked upstairs in my 2-year-old writing the speeds of the carts at the speed of the cart at those 3 locations, the initial location, the final location, and that intermediate far right location. So, for example, I released the cart, I measured this with 0.54 meters per second speed, is towards the right. At the top of the hill, the cart has, I'll play it one more time, when it gets to the top of the hill on the far right, there's a moment, the moment we were interested in, where the cart's actually not moving at all. It's got 0 speed. And then it falls back, and the final moment when I catch the cart, it's moving at minus 0.45 meters per second. It's going in the other direction there, and it's a little slower than when it first started, when I first released it. Okay, I'm going to go back to my slides now, if I'm capable of doing that. And now introduce 2 more terms, and they are velocity and speed. So downstairs here at the bottom of the slide, I've redrawn the reference frame, the motion of the cart, the initial, intermediate, and final positions, the initial, intermediate, final times, but I've also added the speeds at those 3 moments, those 3 instants. So it started with a speed of plus 0.5 meters. Oh, there's a typo here. I've got to correct this. This is bad. This should be meters per second, sorry. The speed over here on the far right, when it turned around, that was 0. And the speed here at this point, the velocity here is 0.45 seconds, meters per second. I'll get these units corrected. So velocity V, I mean, I guess I could correct them now if I was capable. Okay, that feels better for me. Now I've got to put that back in the slide view. The velocity is defined by this statement or this equation. The speed, which is different, is defined by this speed or this statement or this equation. So velocity in physics we define as displacement over the elapsed time for the trip, whereas speed in physics we define as distance over the elapsed time for the trip. So those are 2 different definitions. As a formula, it's delta x over delta t for the displacement, because displacement over time, that's the velocity. And for the speed, it's distance d over time interval. That's for the speed. They both have the same dimensions, length over time. They both have the same units, meters per second, but they are quite distinct. Now, I should make a little quick clarification about them, because sometimes we'll talk about average speed and average velocity. When we talk about average speed, average velocity, all we mean is that time interval for the trip is kind of finite. You know, it's the average speed or average velocity for the entire trip of the car. Sometimes we also talk about instantaneous speed, instantaneous velocity. That's kind of the speed or the velocity at that moment, that instant. And when we do that, we've imagined that we've shrunk that time interval, that delta t, down to nothing, down to almost 0. And so we will talk about speed and velocity with 2 distinct meanings, defined differently in terms of displacement and distance. We'll also talk about instantaneous speeds and average velocities, where the time interval is either vanishingly small or finite. Okay, so let's practice our use of our work with speed and velocity to calculate the average velocity and the average speed for the entire trip of the cart. So to do this, I've drawn again the picture of the cart on the reference frame. I've labeled it with the 3 sets of coordinates, the x1, x2, x3, the t1, t2, t3. And now I'm going to calculate, first of all, the average velocity. Remember, the average velocity for the entire trip will be the displacement for the entire trip divided by the elapsed time for the entire trip. The displacement we previously calculated. So I'm using the result from an earlier slide. It was 1 meter, if you remember. I've got to divide that by the elapsed time. That's 19 seconds. The velocity, the average velocity, it's got this little hat that means average. The average velocity then is 0.05 meters per second. And so that's average velocity, this guy here. Question also asked, what's the average speed? So let me also do that. The average speed, here's the definition of average speed down here. Instead of being the displacement divided by the elapsed time, it's the distance divided by the elapsed time. And so I've got to take the distance for the entire trip, which again, I'd previously worked out and divided by the elapsed time. The distance, if you remember from the earlier slide, was 5 meters divided by 19 seconds. That gives me 0.26 meters per second. And so that's the average speed for the trip. So again, that's an important point. Not only was the distance and displacement different for the trip, 5 meters versus 1 meter. The velocity and the speed are also different. They're 0.05 meters per second and 0.26 meters per second. And that's not surprising because the velocity and the speed are tied to the displacement and the distance respectively. And so a lesson here is that whilst in everyday language, displacement, distance, I think of them as the same kind of thing. Everyday language, I think speed, velocity, same kind of thing. But in physics problem solving, we've got to be careful about this distinction between speed and velocity, between distance and displacement. Okay, here's a graph of this time velocity versus time. The earlier graph was of position versus time, but you can also draw velocity versus time. And so I drew that out. So on this graph, the horizontal axis on this graph is time, like it was in the earlier graph. But now the vertical axis is velocity rather than displacement, position. And you see 3 points. This is the point corresponding to the initial velocity of the cart. It was plus 0.5 meters per second. It's towards the right. Let's see, downstairs over here. This is the intermediate position of the cart. It's where it got to the far right and momentarily had 0 velocity. We called that V2. It occurred at 11 seconds. And then this was the final position of the cart, the V3, and its velocity there was minus 0.45 meters per second. And that occurred at 19 seconds. So these are the 3 velocities at those 3 important times, the initial, final, and intermediate time. But again, there's a horizontal line, there's a solid line here. And this line tells you in detail the velocity as a function of time. And you see the velocity decreasing towards 0 to begin with as the cart goes towards the right. It's 0 at the rightmost point, and then it increases as the cart moves back towards the left. It gets faster, but it's traveling in the opposite direction. Let's see, what am I doing? Clear? Go on to next slide. Okay, an interesting thing is that the earlier position versus time graph and this new velocity versus time graph, I've shown them both here. So, for example, downstairs here, this is position versus time. Upstairs here, this is velocity versus time. I've shown these 2 graphs together, one on top of the other. And I've done that because velocity versus time is actually related to position versus time. Velocity versus time is the slope of the position versus time graph. So if you look over here, the slope is upwards on the position versus time, and it's pretty steep. And that means a large positive velocity up here. At this location here, right, the slope is still upwards, but it's a shallow slope. And that corresponds to a smaller positive velocity. Now over here, at this point, right, now the slope is downwards, the opposite direction. And it's still pretty shallow though. So that would be a small negative velocity here. And now over on the far right, right, the slope is steeper downwards, and that would be a larger negative velocity. So the top graph, velocity versus time, is really just the slope of the bottom graph, position versus time. And where the slope is 0, right, this curve is flat or horizontal at this point here. That's where the velocity is 0, right up here. So those two points coincide. Okay, so not only does Lady Gaga come to class, but so does Brad Pitt. By the end of this class, they may be dating, I don't know. But anyway, here Brad is stressing this difference between velocity and speed. So velocity is a vector like displacement was a vector. And in one-dimensional motion, velocity, displacement can have plus or minus signs, depending on whether it's to the left or the right. Speed, on the other hand, like distance, is a scalar quantity. It doesn't have direction. It only has sign, only has magnitude. And so distance and speed are both scalars. Velocity and displacement are both vectors. So if you walk around the library, and you do a complete loop of the library. When I did this earlier on today, my average speed was 1 meters per second as I gradually strolled around the library. That was the average speed for the whole trip. But my average velocity for the whole trip was 0 because I came back to where I started. Because the displacement was 0, the average speed was 0. Okay, I want to show the demonstration again to show you acceleration. So I'm hoping you can see a new screen. And here I am again. I'm going to try this demonstration one more time. This got quite exhausting. But this time, we're going to watch the acceleration. And I've actually, again, in my 2-year-old handwriting, I've written the acceleration at the initial location, the intermediate location, and this final location. And actually the acceleration, because I measured it, was always minus 0.05 meters per second squared at each of these points. So let's watch the trip now. Remember, acceleration is how we measure or quantify slowing up or speeding down. That's ridiculous. Speeding up or slowing down. And as you look at this cart, as it traveled from the left to the right, I'll rerun it. You see it slowing down, so it is accelerating. And then also as it travels from the right to the left, it's also accelerating because it's then speeding up. So here's really slowing down. Look, that last little bit to get to the top of the hill, that took a while. And then as it turns around, it starts to get faster and faster. And I'll play this one more time for you. Just try and watch that acceleration on the two halves of the journey. Actually, so you might want to do this later. You can play this in slow motion, and you really get a nice feeling for the nature of the motion by watching it, spreading it out over a minute. So slowing down on the way to the right, speeding up on the way to the left. Accelerating both on the travel to the left and to the right and the travel to the left. Okay, I've gone back to my slides now. And So here I want to define acceleration. This is the thing we use to define, for example, speeding up or slowing down. So on this slide, if you look on this slide, I've drawn the reference frame with the cart's motion again, to the right and towards the left. I've written down the positions at that initial, intermediate, and final points, the times for the initial, intermediate, and final points, the speeds for the initial, final, and intermediate points. And now I've added the accelerations at those 3 points, which I also measured. And their values are minus 0.5 meters per second squared for A1, A2, and A3. The acceleration is defined in this way, by this statement upstairs or this formula downstairs. So the acceleration in words is the change in velocity divided by the elapsed time. As an equation, it's delta V, meaning change in velocity, divided by elapsed time, delta T. It's the difference between the final and initial velocities divided by the difference between the final and initial times. And its dimensions are the dimensions of velocity over time. So that's the dimensions of length over time squared. And its units, therefore, are meters per second squared. And it's interesting that in physics, we do use displacement and distance, a vector and a scalar quantity, when describing motion. We do use speed and velocity, a scalar and a vector quantity, when describing motion. But when it comes to acceleration, the description of speeding up and slowing down, we just use this one vector quantity that we call acceleration. Okay. Let me make a little clarification about acceleration that is similar, very similar to the clarification that I made about speed and velocity. That when we talk about acceleration, like when we talk about speed and velocity, we sometimes talk about average acceleration, sometimes talk about instantaneous acceleration. So the average acceleration is over some finite period of time. The instantaneous acceleration is where we think of that time interval as shrinking to nothing. It's the acceleration at that moment as compared to the average acceleration over a longer period of time. On this slide, I'm just going to calculate the average acceleration for the entire trip that took the cart from the left to the right and back towards the left again. Just like we did the same sort of calculations for distance and displacement, we did the same sort of calculations for speed and velocity. So here's my calculation. My calculation is based on the equation for acceleration that's down here at the bottom, and it's that the acceleration is the change in velocity divided by the elapsed time. So that's my formula down here for acceleration. My change in velocity for the entire trip is the difference between the final velocity v3 and the initial velocity v1, and the difference between the final time and the initial time. And so I just fed in the differences between the initial and final velocities. That's in the numerator here. This number is minus 0.99 meters per second. And the difference between the initial and final times, it was 19 seconds total duration for the trip. You have to be careful about signs, again, for the velocity here. The final velocity is negative. It's minus 0.45. The initial velocity is positive. It's 0.54. So when you put in V3, V1, you've got to remember that this V3 is negative. This V1 is positive, and that's why you get this big negative change in velocity. The velocity went from plus 0.54 to minus 0.45. And then here's the acceleration. And this is the same number as the individual accelerations in this case. Look, it's the same number as this guy. same number as this guy, same number as this guy. That's because this was constant acceleration motion. Here's just, we looked at the position versus time graph, the velocity versus time graph. Here's an acceleration versus time graph. And like the prior graphs, in these position, velocity, acceleration versus time graphs, we plot the time horizontally here. But now instead of displacement vertically or velocity vertically, I've got acceleration vertically. This is the initial acceleration when I release the car. This is that intermediate acceleration when it's turning around. It was going right, and then it's going to go left. And then this is the final acceleration. And again, the solid line here, the solid line is actually telling us the acceleration at any instant, any moment, any time as the car traveled from the far left to the far right and back towards the left. So we're seeing acceleration versus time in the solid line. Okay, so I'm looking in the chat. There are some questions that have passed me by. I don't know if I can summarize them. They're about some of the units that I'm using. So let me just reiterate. Distance displacement has units of meters, dimensions of length. Velocity acceleration is defined as a distance or a displacement over time. So it has units of meters per second or dimensions of length over time. And acceleration is defined as velocity over time. So that has units of meters over seconds squared. It's the meters per second of the velocity divided by another second. So you get meters per second squared. And so those units or those dimensions of displacement, velocity, and acceleration are all determined by the relations between displacement, velocity, and acceleration. They're all connected to one another. Clear? Move on. And finally, I wanted to show you not only, finally, in terms of introducing these quantities, not only is the velocity versus time graph related to the displacement versus time graph, but acceleration versus time graph is related to the velocity versus time graph. So if you look at these two graphs I've drawn here, the lower one is that velocity versus time that I drew earlier. Time horizontal, velocity vertical. The upper one is the acceleration versus time graph that I just drew. Time horizontal, acceleration vertical axis. The acceleration versus time graph is the slope of the velocity versus time graph. So here you see velocity versus time graph is sloping downwards. So it's going in the negative direction downwards, and it has some sort of intermediate magnitude. It's not really steep, it's not really shallow. And it corresponds to this acceleration here. If we look at a later time, we notice that it's no steeper, no shallower. It's the same steepness and it's still downwards. So it corresponds to the same acceleration here. And then finally over here, right? It's no steeper, it's no shallower. It's still sloping down. So it still corresponds to the same acceleration. And so constant acceleration, which is a horizontal line on acceleration versus time graph, looks like a straight sloping line on a velocity versus time graph, as the velocity changes in the same way in each time interval. And so that's how those two things, acceleration versus time upstairs, velocity versus time downstairs, are interconnected with one another. Okay, so there's a question from Sarah, which is actually a good question. Will acceleration always be constant for one-dimensional? Let me say, we'll rephrase the question. Will acceleration always be constant for a one-dimensional motion? No. It is in this example. Acceleration was constant in this example, and actually we'll explain why it was in the next class. But acceleration is not necessarily constant in one-dimensional or two-dimensional motion. And so that's a really good point, that I picked an example that involved constant acceleration, but there are plenty of examples that don't involve constant acceleration. So that was a great question, actually. I want to look at an example of the work we've done in today's class, maybe an example or two. I mean, if I shut up right now, I could get on with 2 examples, but if I keep waffling, it'll be 1. So this is a famous story. There's a picture. It's a little hard to see on this overhead, but this is Colonel John Stapp. This is many years ago, more than 50 years ago. And when they were putting together the space program, they wanted to test the acceleration that human beings could survive. And so they strapped him in what looks like it looks like a shopping cart to me, on rails, and they accelerated him with a rocket and then deaccelerated him with a water brake, and basically figured out at what point he passed out. He survived all this, and he was sort of a hero for all of this. But this question is about the accelerations, decelerations that he survived. So if you look at this question, we're told that he was accelerated from rest to 1,000 kilometers an hour in 5 seconds. And then he was decelerated from 1,000 kilometers per hour to 0 to rest in 2 seconds. So you can imagine these are very big accelerations, decelerations. 1,000 kilometers an hour is very fast. You know, that's scale of speeds of planes. And he got there in 5 seconds and he stopped in 2 seconds. So let's calculate his average accelerations for those 2 portions of his trip. And I'm going to do the calculations in meters per second. So that's what I'm doing on this slide. I've got 2 calculations here. And we're going to calculate the acceleration on the first part of his journey, second part of his journey. And I've depicted his journey here. And I've kind of tried to use the same notation as our demonstrations with the car. Well, there we had sort of the starting location of the car. We had an intermediate location when it got to the far right, and then with the final location of the car. And the same thing in the Colonel John Stapp's trip, right? He started from rest, he was accelerated to 1,000 kilometers an hour, and then he was brought back to rest. And so I've pictured that on this slide here. Here's his initial coordinates. Time is 0, and the initial velocity is 0. I labeled them T1, V1. Here's the intermediate coordinates. Took 5 seconds. He's now traveling at 1,000 kilometers an hour. I called them V2, T2. And then here's his final coordinates. The time now is 7 seconds. That's 5 plus 2. And he's back at rest again. And I labeled those as V3, T3. So here I'm first calculating the initial acceleration for the first part of the journey. And so I'm going to work with, so I want the initial acceleration, which corresponds him from going from rest to 1,000 kilometers an hour. So the change in velocity, there's two things I need, the change in velocity and the change in time to calculate acceleration. Change in velocity is 1,000 kilometers an hour, but I actually then converted it to meters per second. So I didn't write that out in detail, but of course, I changed the kilometers to meters by multiplying by 1,000, and I changed the hours to seconds by dividing by 3,600. So that's how I got this number. And then the time interval, that was simply for the 5 seconds. And so to calculate the acceleration here, all I have to do is divide the change in velocity by the change in time. 278 meters per second divided by 5 seconds comes out to be 55.5 meters per second squared. Now, if you're like me, maybe you don't know exactly whether that's a big acceleration or a small acceleration. Here's a way of figuring out. The acceleration of gravity, if you jump off a building, your acceleration of gravity, don't do it, but if you jump off a building, your acceleration of gravity is 9.8 meters per second squared. I changed the units of 55 meters per second squared for acceleration into units of accelerations of gravity. And I did that by dividing by 9.8 meters per second squared. And I find that his acceleration for the first part of the journey was just under 6g, just under 6 times the acceleration of gravity. So he was like jumping off a building and not falling with gravity, but falling with an acceleration that was 6 times gravity. That's a big acceleration. I also did the calculation for the second stage of the journey. So let's take a look at that. Here it is. So I'm now calculating the final acceleration. And the final acceleration is from here to here on this picture. This was the initial acceleration over here. And in this case, the change in velocity, so I need again the change in velocity and the elapsed time. The change in velocity is now minus 100 kilometers an hour because he's going from 1,000 kilometers an hour down to 0. So it's negative. Again, I changed the units. I wasn't going to work in kilometers an hour. I'm going to work in meters per second. So it's minus 278 meters per second. And here's the elapsed time. The elapsed time is not 7 seconds. That's the final time. It's the difference between T2 and T3. It's 2 seconds. So that's the elapsed time for the deceleration part of the journey. And so then I go to the same little magic formula. Change in velocity divided by elapsed time. Change in velocity is minus 278 meters per second. The elapsed time is now not 5 seconds, but 2 seconds. You get a minus 139 meters per second squared for the acceleration. And if you convert that into G's, units of accelerations of gravity, comes out to be even larger, right? We had just under 6 Gs before. Now we've got just over 14 Gs. Now, one has a plus sign, one has a minus sign, because the accelerations were in the opposite direction. He was speeding up and his acceleration was to the right on the initial part of the journey. He's slowing down. His acceleration is towards the left on the final part of the journey. But also the magnitudes are bigger. It's more than twice as big on the second half of the journey. It's half as small, smaller than half as small on the first half of the journey. That's because the time intervals were different. He sped up in 5 seconds. He slowed down in 2 seconds. Okay, I think I'm going to finish here. We've walked through the language of one-dimensional motion in terms of displacement and distance, speed and velocity, acceleration. That's how we describe, how far something is, whether it's close or far, how fast something is going, whether it's slow or fast, and whether it's speeding up or slowing down, it's acceleration. That's our language in physics.